Okay, now given the understanding of the divergences of Feynman graphs that we just discussed, let us discuss some implications of that. Recall how the divergences appear, what kind of divergences appear depending on the value of the mass dimension of the coupling delta n. And there are three possibilities. One is delta n greater than 0, then delta n is equal to 0, and delta n less than 0. So in the formula for superficial degree of divergence, delta n comes with a minus sign, which means that, and multiplies the number of vertices, which means that when delta n is greater than 0, then larger the V, more convergent is the graph. So larger V implies more convergence. For delta n is equal, for when delta n is equal to 0, the omega does not depend on the number of vertices. It's independent of V, and divergence appears only up to a cutoff value of the external legs, number of external legs. And when it is less than 0, delta n is less than 0, then as the number of vertices increases, divergences become more severe. Now, of course, in these two cases, the first two cases, it's clear that the spectrum, so in the first case, we see that when V increases, the diagrams become more convergent, which means omega tends to become more negative. And in this case, it does not depend on V, but when we increase the number of external lines beyond the threshold cutoff value, omega becomes negative. So the spectrum of omega greater than or equal to 0 must be finite for these two cases. This must be finite in this case, in these two cases, but it should be infinite in this case, because in this case, more we allow a larger number of vertices, we tend to receive more and more severe divergences. So that will correspond to higher values of omega. And but this is the spectrum of omega. That doesn't mean that the spectrum of omega should be the graphs, corresponding graphs. The spectrum of graphs should also be finite for the first two cases. So let us look at that. So in this case, let us consider first omega greater than or equal to 0 graphs. What kind of graphs can have omega greater than or equal to 0? And there are two cases here. There are two types of graphs. One is primitive graphs denoted as curly p,
So these graphs are primitively divergent. So what it means is that the graph itself has omega greater than or equal to 0. The graph is divergent, but the graph does not have a subgraph divergence. So which means the graph is small enough not to have a subgraph which is divergent. So it is like a smallest unit of divergence corresponding to a given positive or zero value of omega. Then there are other graphs which have non-primitive divergences. Their omega is greater than or equal to 0, but the divergence is coming from a subgraph. So let me denote them by curly E. They are they have non-primitive divergence. Now it turns out that the spectrum of curly P is finite in all the three cases. We shall argue that why exactly that is so. There is a precise argument for this, but let's now assume that for the moment. Now, for the case of it is easy to understand for the first case where the divergence, there is a restriction to what we can get for as spectrum of omega. If we increase number of V's, then omega will increase, and therefore there will be only a finite number of graphs for which we will get this divergence. Since the spectrum of omega is finite, and there is a restriction that it must come from a primitive, like there should not be any subgraph. That is quite it is quite implausible that the spectrum of such graphs is finite. But that's not the case for curly E, because in curly E, the divergence can come from a subgraph, and in fact should come from a subgraph. That means there are other parts of the graph, and if you add more structure to the graph, if you pick one element from here, and which becomes a subgraph in a more complicated graph, and that graph does not change the value of omega, it still remains, it doesn't change the value of omega in the negative direction. So it still remains omega greater than or equal to 0, but it is bigger than this kind of a primitive graph. Then question is that whether there is a restriction of how far I can do that. In case of this one, delta n equal to 0, you see you can keep on increasing V without affecting the value of omega, which means you are adding more and more vertices. The omega does not change. If you keep E fixed, then you can create more and more complicated graphs with the same value of omega. And those graphs must be having, because omega greater than 0, greater than or equal to 0 is necessarily divergent, those graphs must be divergent. And so there can be many more diagrams for the same value of omega with higher and higher values of number of vertices, and they are non-primitive because the divergence must be coming from some subgraph which is identical to this. So that there is no control over how many such graphs. There is no restriction, and therefore the spectrum of non-primitively divergent graphs is not finite in this case. In this case, it is of course not finite, because the spectrum of omega itself is not finite. So what we arrive at the following statement. It is finite in the first case, because we couldn't do this process what I just explained. If you increase the number of vertices to make a bigger graph on top of this primitive graphs, then it will become more convergent. So so the adding more vertices or making the graph more complex or bigger will push the value of omega towards the negative side. So that is why there is an upper limit. There's a restriction on the how many E kind of graphs, curly E kind of graphs can we get. So that's why it is finite. So both P and E are finite when delta n is greater than 0. But as I just explained, this is infinite for delta n equals 0 and delta n greater less than 0. Okay. Okay, now the question is, what kind of other graphs can we have? So these are all the discussion about omega greater than or equal to 0 graphs. So any other graph will have negative omega. And so any other graph, all other graphs have omega less than 0. And there are two types of such graphs. One is, this is coming from Weinberg's theorem on this. One is overall finite. These are graphs which have omega less than 0, negative superficial degree of divergence, but the graph has graph is divergent because of P or E type of subgraph. Right. This is Weinberg's theorem, which says that this is not, we just discussed in the previous slide, that this is not enough. The omega being negative is not enough, that the graph will be enough to guarantee that the graph is convergent. And the graph can be divergent even if omega is less than 0. And that is the case for overall. Those are the graphs which are called overall finite. And they are divergent because there are subgraphs which are divergent. And as we just classifies the divergent graphs, these are of P or E type. And the last category is absolutely finite. This means they have no subgraph divergence. Okay, now let us look at what are the P graphs, what are these properties, and why is this finite in all the three cases. So let's focus on P graphs. So in this case, divergence occurs in loop momentum. So the divergence is always occurs, as we know, in loop momentum integration. And the general structure of that is the following. How such a divergence appears in a loop
that you have a loop, and then that loop is part of the entire graph, and therefore is connected to the graph through certain vertices. The number of vertices, say 1, 2, and so on, up to say p number of vertices. So if there are p vertices that are held up by the loop, then there are p propagators associated to them. Okay, so this is a loop with p propagators or vertices. For such a loop, the momentum integral will be of this form, Euclidean momentum integral. So it's a d-dimensional integral, and in the denominator you have L bar squared to the power p, and in this RC region, it will look like the following: d minus 2p minus 1, and therefore omega is equal to d minus 2p. Right? So basically what it means, for each loop you have d power of momentum in the numerator, and for each propagator you have k square in the denominator. So that is d minus 2p. So that is the primitive, that is the divergence, omega, I mean superficial degree of divergence. So this divergence will occur when p is between 0 and d by 2, right? Then omega will be greater than or equal to 0. That corresponds to omega being greater than or equal to 0. So let us look at this this terminal value, p equals 0. The p equal to 0 means there are no vertices, and therefore it is actually, the entire graph is actually a loop like this. This is the entire graph, because there are no vertices with which it is connected to a bigger graph. This is the entire graph. But this does not appear in the generating functionals, as we have seen before. So does not appear in generating functional W or Z, because it is eliminated by the proper choice of vacuum. Recall that W at j equal to 0, which is a vacuum graph, is always 1 by definition, and therefore it doesn't occur. Okay. However, this is a valid topological graph that one could draw even in a free field theory, and one has to interpret. And the interpretation is that it doesn't appear because of the proper choice of the vacuum, and we know in free field theory the vacuum is chosen by and that is taken care of. The divergence in free field theory, when we define operators, we actually remove, for example, in the Hamiltonian,
we remove a divergence by normal ordering it. Without normal ordering, operator with normal ordering and operator without normal ordering will differ by a divergent piece, and it is this divergence, and which is eliminated by the choice of vacuum. So normal ordering removes divergence. Divergences in the vacuum expectation value of various operators. Here, here the choice of vacuum eliminates this diagram to appear from the generating functional. And okay, let me finish it.